So let's talk about the origins of chemistry. The word chemistry comes from the word alchemy. Alchemy was a pseudoscience that was practiced in China and India since 400 BC. And alchemists were essentially trying to do magic. They were trying to turn things that weren't gold, like metals like lead, into gold. They obviously didn't succeed in their attempts, but they did develop a lot of the tools and techniques for working with chemicals. This is a picture showing all the different instruments that were invented by alchemists that were trying to do magic and failed miserably, but they invented all the things that we still use today in the chemistry laboratory, or we use something similar to them today. So in the 1500s, there was a shift away from alchemy to actual science. King Charles II was a big supporter of the sciences. There's King Charles. And he founded or helped found the Royal Society of London for the Promotion of Natural Knowledge. It's these guys here. It's a bunch of noble people and scientists who would get together and talk about science stuff. And they didn't just talk, they encouraged scientists to use experimental evidence and not just philosophical debates about these things. This is the official seal of the Royal Society for London, and at the bottom you see in Latin it says nullius in verba. My Latin's not the best, but it roughly translates to something like don't take anyone's word for it. Do your own research, get your own data. In the late 1700s, Antoine Lavoisier helped transform chemistry from a science of observation to a science of measurement. Till that time, they were just doing these experiments and observing what was happening, but they weren't actually quantifying or measuring their results. There's Antoine with his wife. He actually designed a balance that could measure to the nearest 0.005 grams, which is really small, a lot more accurate than the scales we even use in lab. He was able to settle a long-standing debate about burning, which was that oxygen was required. He invented a little vacuum chamber to prove this. So next we're going to talk about the scientific method. This isn't how every scientist goes about answering problems. It's not a rigid stepwise fashion that I'm about to present to you, but it can be this way. So scientific method is a logical, systematic approach to a solution of a scientific problem. Here are the steps. First, we need to make observations about the phenomenon we're looking at. Then you need to propose a hypothesis to explain that phenomenon. You need to test that hypothesis using a controlled experiment. And then you develop a theory about based on the results of your hypothesis test. So first we need to make an observation. An observation is when you use your senses to obtain information. This information can be qualitative, which is a word descriptor like the fire is hot. Or it can be quantitative, which uses numbers like the flame is 95 degrees. Observations can often lead to questions. Then we propose a hypothesis. This is a proposed explanation for that observation, a proposed answer for that question that you may have come up with based on your observation. A hypothesis is usually based on prior knowledge. Usually have some background knowledge about your hypothesis you're making before you make it. Your hypothesis also must be testable by an experiment. So let's talk about how we test those hypotheses. We set up an experiment. This is a procedure that's used to test the hypothesis. A hypothesis can only be supported or refuted by experimental data. We don't say it's proven right or proven wrong. We say the data supports our hypothesis, meaning our guess was supported by the data we obtained, or refuted, which means it doesn't support it. It doesn't necessarily make it right or wrong. If the data does not support the hypothesis must be changed, and you start again from the beginning with a new experiment. When testing a hypothesis, we need to design a controlled experiment. Controlled experiment is a test in which the experimenter only changes one variable at a time. That way we know whether that variable was significant in the differences that we may or may not see in our results. So the independent variable is the variable that we change. The dependent variable is the one that we observe, or the one that we measure. Everything else is a control or a constant. It's everything that stays the same to prove that that one thing we changed, our independent variable, was responsible for any changes or any differences we see in our dependent variable. So let's do an example. We're going to design a control experiment to test how plant fertilizer affects plant growth. So we need two groups. We need a control group and that we're just going to give water, and we need an experimental group that we're going to give fertilizer. Remember, we want to see if the fertilizer is making a difference. So we need to compare it to a control which isn't going to get the fertilizer. We're going to put the same plant in each pot, and we're going to measure any differences that we see here. So we see on the left the control plant grew to about 3.5 inches, and on the right the experimental plant grew to about 6. So let's list our constants. Our constants, remember, are the things that stay the same, that we don't change in the experiment. We use the same plant. We use the same amount of light exposure, same exposure to the sun. They should have the same soil, and the same volume of liquid should be given to the plant each time they're watered. They should also be in the same temperature. If all of these things are the same, we can know that the difference we see in the height is responsible only due to the fertilizer that we gave them and not some other outside factor. So our independent variable, the one that we changed, was the fertilizer. That's the only thing we changed. Everything else was a constant. Our dependent variable is the thing that we're measuring, which is growth in inches. Okay, now let's see how this would look on a graph. So you need to be able to set up your graphs appropriately based on the experiments that you design. So on our axes here, we have our y and our x. Our dependent variable always goes on the y, and you can make a little d from that line there to remember. Our independent variable goes on the x, and you can make the little I on that line to help you remember that as well. So our independent variable was the fertilizer. So we have two groups. We have our control and we have our experimental group that had fertilizer. So fertilizer, no fertilizer. That was our independent variable. Another way to help you remember this is this little phrase: I control the independent variable. I controlled how much or whether or not the plant got fertilizer. I don't control how much it grows. That's what I measure. That's what goes on my dependent variable. So you always want units as well, if applicable. So we have growth in inches on our dependent variable on our y-axis. And we want a nice even scale. I don't have any numbers here, but when you do, you would have a even scale. Okay, and there's our data. Our control group grew a little bigger than 3 inches.
Let's look at what can happen over the long term of our scientific discoveries.
It can lead to a theory, which is a well-tested explanation for a broad set of observations. We don't say that we prove or disprove theories, just support or refute based on the data that we've collected. It doesn't mean it's unreliable, however. It could also lead to a scientific law, which is a concise statement that summarizes the results of many observations and experiments, such as the law of conservation of mass. In chemistry, this is something we're going to talk about. It simply says that in any chemical reaction, the mass of the reactants is equal to the mass of the products. We don't create any mass, we don't destroy any mass. So that's a law. That just says what happens. It doesn't say why it happens. It's not a theory. A theory would be an explanation for why mass isn't created or destroyed. A law just summarizes that mass is not created or destroyed. So like I said, a law summarizes what has happened. A theory is an attempt to explain why it happened. So let's look at the development of a scientific theory. It all starts with an observation, and the observation leads to questions that we will create with a hypothesis. A hypothesis will lead us to an experiment. If that experiment does not support our hypothesis, we will revise our hypothesis and try again. But over the long term, if our experiments do support our hypotheses, that can lead to a theory. And theories can be tested by further experiments. But if we keep getting the same result every time, the same experiments support the same theory over and over the long term, that can lead to a scientific law, such as the law of conservation of mass or the law of gravity, something like that. Also, in the world of chemistry, there has to be collaboration and communication. We have to be able to work with others and communicate the things that we've learned in our scientific discoveries. So when scientists share ideas by collaboration and communication, it increases the likelihood of success. It also saves time. We don't need to do the same experiments over and over if somebody's already done them. It's often necessary to bring people together from other disciplines. That's the collaboration part. It's not always a smooth process, and you probably know this from working in groups. You'll be working a lot in groups this year in lab. It's not always smooth, but it's very important for success in the science laboratory. And then communication in science is done through scholarly publications, like you see here, the journal Science and the journal Nature are two of the biggest ones that if you discover something in science or chemistry, you write it up in a paper and send it to these publications, and they publish it for other scientists to read and learn from. Communication is also done through conferences. This is a science conference where a lot of people have come together to learn about new discoveries that are happening around the world. Sometimes they listen to speakers speak. Sometimes they share their own work through these poster presentations where you can walk around and learn from other laboratories and what they're doing. Communication in science is also done through popular media. There's lots of TV shows like The Cosmos by Neil deGrasse Tyson, teaching about the science of space. It's a very good show. It has also a lot of good chemistry in it. Communication is also done through the internet. Sites like Live Science, even BuzzFeed, New Scientist, Scientific American, National Geographic, Science Daily, Chemistry World. These are all sites that you could go to today and learn about science that you're interested in a way that makes sense to you. This is not written for the professional. This is written for the lay person, students, and non-PhDs. Okay, so let's wrap things up here. Scientific method is a logical, systematic approach to solving problems. Steps usually involve making observations, proposing and testing hypotheses, and developing conclusions and theories, but not necessarily in that order. There's lots of different routes that scientists can take to making discoveries. You also are going to need to be able to set up a controlled experiment. You should have, you should be able to set up a proper controlled experiment, including a control and experimental group and constants that you keep the same, and labeling axes appropriately. Remember, the independent variable is the one that you change and you have control over. The dependent variable is the one that you measure. Always goes on the y-axis. And you should also know how and why scientists collaborate and communicate. Hope that makes sense, and if you have any questions, please let me know.